So, and today, can we keep the class for 1 hour?
1 hour.
Yes, sir.
Um, yeah, okay. So, okay. So, yeah, do you have some urgent work?
No, sir. I just have to study for biology, right? It's tomorrow.
Oh, tomorrow. Yeah, so I will keep it 1 hour.
Okay, sir.
So, let me just so we discussed what is the potential energy of a single charge in the presence of external electric field, right?
Yes, sir.
But let's say that we have two charges, right? We have two charges. Then in that case, what is the potential energy, right?
Yes.
So let us talk about. So if we have technology charges in the presence of external electric. Right. So what do we have? We have external electric field. Right. And due to this electric field, yeah, there would be some potential. Right. How the potential is related. So potential is simply minus E dot T. Right. From infinity to some fixed. That is so. Yeah. Let's find out. Let's say we have two charges. Let's say this is Q1 and this is Q. Right. So at these
Yes.
2 points, there would be potential and there would be another potential. The separation between these 2 points is out. So then in this case, what is the potential? So potential energy, one would be due to this charge and potential that is Q1 lever. Then due to this charge, that would be Q2 V2. And then we have the interaction between these two charges. That is A, Q1, Q2 by. So that is the potential energy of two charges in the presence of electric charge. Is it clear?
Yes.
So now let us talk about the potential energy of a type in the presence of electric charge. So potential energy right. So what do we have? We have electric field, external electric field, and we have a type. So what is the dipole? Dipole is minus Q and plus. And then the separation of this dipole is, let's say, Q1. So this is the dipole, right?
Yes, sir.
So we know that, let's say, what is the work done, because this is a dipole, right? And this is present in the presence of this electric field. So it will experience some torque, right?
Yes.
And do you remember what was the torque? Do you remember? is the external torque? Or what is the torque of this type? What is the torque in the presence of electric torque? Yes.
You
That was P cross E. Right. So this torque was P E sine P. Right. And what was the direction of the torque? So we place this is dipole moment. Right. This is electric field. This is theta. So this was P cross E. So that was in the downward direction. Right.
yes, sir.
So this was the torque. Now, if I want to rotate this thing, right? So if I want to rotate this thing from here, let's say from theta 1 to let's say some theta 2 angle. Right. So what is the work done in rotating the dipole from theta 1 to theta 2? Because you see that the linear one we cannot make because this is the force are balanced. So it has net force 0, it can only have this torque. Right. So work done would be how much? Work done in moving this thing, that would be tau external dot d. Right.
Yes, sir.
And we know that what is this tau? This is this torque. So this is simply P E sine theta. And then d theta. Right. So this is d theta. And the angle between this torque and this theta is how much? That is 180. This is from theta 1 to right. Is it clear?
Yes, sir.
Okay, so this would be how much? So this is cos 180. So that would be minus 1. So this is minus PE sine theta, d theta, and this is theta 1 to theta. Right. And this is the work. So if I write what is the integration of so this is theta 1 and theta 2. What is the integration of sine theta? Yes, what is the integration of sine theta? Yeah. What is the integration of sine? That is minus cos theta.
Minus cos x.
Minus cos theta. So this is theta 2, theta 1. And then this minus and this minus will become positive. So this is PE and cos theta. And then we have to put theta 2 and theta 1. So this is PE cos theta 2 minus cos theta. Right. And
Yes.
if we assume theta 1, right? So what we are doing is that we are bringing this thing from here to here. So we are bringing this thing from theta 2 to theta 1. So let's say that theta 1 is 90 degree and theta 2 is 0 degree, right?
Yes, sir.
Or let's say that, yeah, because we are bringing this thing from this theta 1, right? This is the angle. Theta 1 to this theta 2. So theta 1 is 0 degree and theta 2 is how much? That is 90 degree, right? So then what would be this? So this would be PE and cos theta 1 is how much? Or cos theta 2 is how much? Theta 2 is 90, right? So this is
Yes.
90 and minus cos theta 1 is 0 degree, or we can make it some arbitrary angle. So let's make it some arbitrary angle here. Right. So then this thing would be how much? Some cos theta. So cos 90 is 0 and this would be minus PE and cos theta. So this is the work, right? And we know that what is this P cos theta? So this is simply P dot E. So this is the work done, and that is equal to the potential. So this is equal to the potential. Okay, is it clear to you?
Yes, sir.
Yeah. So this is the potential energy of the dipole in the presence of the electric field. You know that what is the torque? So torque is P cross E, and potential energy is minus P dot. Okay, so this is how we solve this. This is what is the potential energy of this. So please note it down, and if you have any doubt, please there too.
Okay, sir.
Yeah, derivation is not that important. This result is important. The potential energy is minus P dot. So this is the thing that we have to. Okay.
Okay, sir.
Yeah. So please note down from here. Whenever you want me to scroll down, please.
Okay.
Yeah, whenever you want me to scroll down, please.
Okay. You can scroll down. You can scroll down.
Yeah, whenever you have done. Okay, so
Yes, sir.
just remember that potential energy dipole is simply Q dot, right? And work done is minus PE and cos theta P minus cos theta. So only remember this. Okay, and yeah, the torque is simply Q plus. So these are the things that we have. Okay. Derivation of this part is not very that. Derivation of this thing. So this potential energy is done and almost time we can half an hour. So then we can talk about the potential of a hollow sphere, right? Or this hollow sphere can be solid, conducting. One is hollow sphere that can be conducting or non-conducting, or we have a solid conducting sphere. So for both the cases, the charges will be distributed at the surface. That we already did, right?
Yes, sir.
So then what is the potential of this thing? So there are three potential. One is inside, then at the surface, then outside. So you have to remember that the inside simply KQ by R. Let's say the radius is R. And V surface. This is same as V inside, so that is also KQ by R. And V outside. Okay, let me write this as I want to find out the outside is this, the variable. Right, so V outside is KQ by. So remember, this one is variable. One is fixed. So radius R is always same. Right, this is fixed. So this R is not changing. Not changing. And this one is variable. So if you plot this graph, so if we have V versus potential which is varying with R, and this is R. So this is the variable, right? And let's say that this is R equal to R point side, which is R less than R. This is R greater than, which is outside. So inside and surface, that is constant, PQ by R. Right. So what is the graph of a constant line or constant function? What is the graph? So if I want to draw a constant graph, what would be that? This is the constant, right? It is not changing.
Yes, sir.
So this is a constant, and then it is varying as 1 over r. So this is different. The graph would be something like this is constant. Is this point clear?
Yes, sir.
So please note down this thing. This is important. Potential of a Hall or sphere of conductors.
Okay.
Here we have our whenever you have not used to.
Okay, sir. Yes.
Yeah. Okay, so this potential energy and potential, that part is right. So we have understood all the kinds of work done, right? And then we related work done with potential. Then we related work done with electric field. Then we related work done with potential energy, right? So all these things we have. So potential we have calculated for different systems. And again, we have calculated work done in the presence of electric field, then related how the potential and electric field are related, and all those things we are. So please go through that. If we are those things, and if you have any doubt, please.
Okay, sir.
Okay, so the next topic is capacity.
Yes, sir.
So what is the capacitance? So it is the energy storing capacity of some material. And that is what we call the capacitance, right? And it is only dependent on the geometry of the object or material, and then it is independent of charge and voltage of T. Right.
Yes.
Its SI unit is, we write it CV inverse, right? Or Farad, which is denoted as, right. So, and then it is a scalar quantity, right? So how we calculate, how we can mathematically represent it? So Q is directly proportional to voltage. If we remove this proportionality, so we get this capacitance, and this is what we call the capacitance.
Yes.
Right. So this capacitance is independent of voltage. So if we have this capacitance and we have this voltage, so this is a constant, right? And this is also independent of charge. So for this thing also we have a straight line, right? So both these cases are showing that this is a constant. Okay. So what are the devices that use this idea of capacitance? Those are called the capacitor, right? So we have a capacitor. And what are capacitors? So they are energy storing device. Right. And what kinds of capacitor do we have? So we have parallel plate capacitor. We will talk about this thing extensively. We have spherical capacitor. And then we have cylindrical capacitor. Not in CBSC. Right. And this one is one example that we want to talk about. This is the syllabus. So with this one, we will talk about extent. Right. So please note down these things and we'll talk about the other things. Right. And if you have any doubt, please tell.
Oh,
Yeah, whenever you want me to scroll down this step.
Okay, sir. You can scroll down. Done.
Okay. So now, before we talk about this parallel plate capacitor, let us talk about first spherical capacitor. So spherical hollow capacitor. So we have a capacitor, right? And this is the capacitor. Its radius is r, right? And we want to find out the potential at the we want to find out the potential at the surface. So you already know what is the potential at surface. We have just talked about this thing, so this is simply K2 by, right?
Yes.
And what is the capacitance? That is Q is the charge is C. So if we calculate this C, so this is the potential at the surface. So this is Q by V. We already know the value of V, so if we put that, so V is KQ by R. This Q and this Q will cancel. This K is 1 by 4 pi epsilon naught. So it will go upstairs. So this capacitance will become 4 pi epsilon naught. So this is the capacitance of a spherical capacitor. Is that clear?
Yes.
So quickly note this thing.
Done.
Okay, now we can talk about the parallel plate capacitor. So we have a parallel plate So this is denoted by, so we have this thing, right? This is connected to positive terminal and this is connected to negative terminal. Or we can represent it as this one and this is ground. Right, so this one would be positive and this one is negative. Right, so this is how we make this random pictures. Right, or let us write only the, so representation is parallels. Right, so this is made up of two sheets. One sheet has positive charge, the other sheet has negative. Right. Now, now what do we have? So for this positive sheet, do you remember what is the electric field of thin sheet? What was the electric field of this thin sheet? Yes.
I didn't understand the question.
Yeah. So what is the electric field of a thin sheet? Using the Gauss law, we derived the electric field of thin sheet. Yes, using the Gauss law, we derived the electric field of thin sheet. Right?
Yes,
So
so
that
those are-
was sigma by 2 epsilon.
yes.
So if we have a thin sheet, right, say this is positive. So it will have sigma by 2 epsilon naught this side and sigma by 2 epsilon naught this side. So this will be electric in both the sides. Right. If we have a negative sheet, so for this case, it will have sigma in the right hand side, sigma by 2 epsilon naught, and in the left hand side, so that would be income. This is out. Right, so this is again sigma by 2 epsilon. These things we have talked about in the first chapter. Okay.
Yes.
So now we combine these two sheets. That is the idea of parallel plate capacitor. So we have this positive one. For the positive one, the electric field will be outside, going away. And we have three regions. This is first region, second, and third. So if I talk about this positive one, so in this first region, where would be the electric field, left or right? For this positive one. Yes, in this region, the electric field would be left or right for this positive field.
On right.
You see that electric field is going away from this sheet. For positive, it is going away from this sheet. Right.
Yes.
So in this direction, in this region, for this positive sheet, so that would be going away. Right.
Yes.
So this is E, which is sigma by 2 epsilon. Let's say this is E1. Due to this positive. Okay. In this region, the fields would be in the right hand side. Again, going up. And that is again sigma by 2 epsilon. In this region, again, that would be in this side. Again, sigma by 2 epsilon. Now we have this negative plate. So for negative plate, what would be the direction in this first region? Left or right?
It's left.
Yes,
It's left.
it's left. Left is going away from this plate. For negative
Yes, sir.
1, the electric field is coming towards this sheet. So that would be right. Right, this is clear.
Yes, sir.
In this region, in the second region, due to this -1, the electric field would be away or towards the plate. Yes,
Yes,
we are
it goes
talking
left.
about this. Yes,
It goes left.
left. Why left? That would be away. This -1, so that would be towards its side.
Oh, again.
So this is sigma by 2 phi. Now we are in this third region. Third region due to this negative plate. So that would be away or towards its side. Yes,
It's right.
it's right. Right would be away from this plate.
Yeah, this
That
is
should
left.
be towards. So you see that we have three regions. The purple one shows that for the positive one, this would be away, this would be away, this would be away. So these three are away. And for the negative plate, all these regions, that would be towards its side. So this is towards its side, right? So this is towards. So you see that in the first region, one is going left, the other one is going right. So that will cancel. This region, total E is E1 plus E. Right, that is adding up. Both are in the right hand side. And this one E net is 0. And this one also E net is 0. So in the first region, E net is 0. In the second region, E net is sigma by 2 epsilon naught plus sigma by 2 epsilon. So E is simply sigma by 2, sigma by 2. So this is sigma by epsilon in the second region. And in the third region, the net is again 0. Right? Is this part clear?
Yes, sir.
So please note down this thing and then we'll, yeah, and then we'll take 2 or 3 minutes more. Then I'll stop.
Okay, sir.
That, what? So we can extend it to 15 minutes more, right? We have 15 minutes, let's extend it.
Okay, sir.
15. Yeah. So whenever you have please do.
Okay, sir.
Yeah, whenever you have multiple pairs.
Done.
Right. Yeah, so can we extend it to 15 minutes more? Or do you want to stop? Yes?
Sure, sir.
Okay, so now we have calculated the electric field, and now you see that this is not a line. This is a sheet, right? So we have two sheets, right? Now we want to find out capacitance of parallel plate capacitor. So we have these thin sheets, right? And let's say that this one has area. So both of them have the same area, right? This area and this area. This area is A, and this is also A. The distance between these two plates is E, right? And we know that we have just calculated that electric field is 0 in here. Electric field is sigma by epsilon naught in here. Electric field is 0 in here. Right.
Yes, sir.
Now, what would be the potential between these two plates? So what is this is, let's say, plus Q. This one is plus and this one is minus. So let's say that the potential between these two plates is V, right? So we know that potential is how much? That is E and L, right?
Yes, sir.
So this is the potential. And we know that we have just calculated what is the electric field. That is sigma by epsilon naught T. So this is the potential. And we know that capacitance is how much? Capacitance is Q by V. Right.
Yes.
And we know that this Q is, or we can write this, this is sigma by epsilon naught into V. So this would be how much? This would be Q, and this is sigma D into epsilon. We know that this sigma is how much? This is the surface charge density.
Yes.
And how much this thing? So this is Q by A. If we put this value in here, so this would be Q epsilon naught. This is Q by A. And then this is T. So if we simplify this thing, so this would be Q epsilon naught A divided by, because this will go upstairs. And this is Q into Q. So Q and Q will cancel and we'll get A E epsilon naught by. So this is the capacitance of parallel plate capacitor.
Yes.
Okay, so please note it down and then we'll stop. So we'll stop. Please note it down.
Oh,
Whenever you are please.
okay.
Yeah, whenever you have okay, please do.
Yes, sir, done.
Yeah. Okay, so all the best for your biology preparation and yeah, we'll also arrange some extra classes so that we can finish we can start the program also. So whenever
Oh,
your biology exam ends, so then there will be the next exam would be physics, right?
no, sir. The next exam would be English.
Oh, in English. So you don't require